Half of the normal matter in the cosmos has simply vanished. This is not dark matter, but the ordinary atoms that should make up every star, planet, and person. Astronomers call this the Missing Baryon Problem, and it stands as one of the greatest scientific detective stories of our time. By the end of this journey, you will possess the 25 crucial clues that are guiding us to the answer. Where could an entire universe worth of atoms be hiding, and what does their discovery mean for our understanding of everything? The solution is closer than you might think. What does it say about us that we can lose something so fundamental? Our story begins not with a flashy telescope image, but with a single, stubborn number. It is the universe's total density of ordinary matter, a figure cosmologists call the baryon density. This number is etched into the oldest light we can see, the cosmic microwave background. That faint afterglow from the Big Bang, a snapshot of the cosmos when it was just 380,000 years old, tells us precisely how much normal stuff the universe started with. It is a cosmic birth certificate, and it is incredibly precise. According to that ancient light, about 5% of everything in the universe should be the familiar protons and neutrons that build atoms, planets, and us. That is the cosmic inventory. It is the total amount of baryonic matter the universe was issued at the beginning. Now, fast forward nearly 14 billion years. Astronomers, armed with ever more powerful telescopes, began to take a modern census. They added up all the luminous matter they could find. They counted every star in every galaxy, every wisp of glowing gas in the vast spaces between them, every particle swirling around black holes. They tallied it all with meticulous care, and when they finished their grand cosmic accounting, they came up short, dreadfully short. The sum total of all the ordinary matter we can directly observe in the present-day universe amounts to only about half of what that cosmic microwave background says should be there. Roughly 50% of the protons and neutrons, the very building blocks of the visible cosmos, are simply missing from the ledger. They are not in stars. They are not in galaxies. They have to be somewhere, but our telescopes, tuned to see light, were staring right through them. This glaring mismatch between the ancient record and the modern inventory is the foundational clue, the discrepancy that launched the entire mystery. We had a universe's worth of material on the books, but half of it was unaccounted for in the present day. The hunt for where it went and what form it now takes had officially begun. The leading suspect in this cosmic case is not a place, but a state of being. It is a form of matter so diffuse, so energetic, and so elusive that it has escaped our notice for decades. Astronomers call it the warm-hot intergalactic medium, or the WIM for short. Picture the universe not as a collection of isolated islands, but as a vast three-dimensional spiderweb. Galaxies and galaxy clusters are the dense knots where the silk is thickest, but the true structure, the scaffolding that holds the entire cosmic architecture together, is the web itself. The WIM is that web. It is a filamentary network of incredibly hot gas threading through the immense voids between galaxies. This is not a gentle mist. This gas is superheated to temperatures of hundreds of thousands, even millions of degrees. At such extremes, atoms do not behave as they do here on Earth. Electrons are ripped from their nuclei, creating a seething, thin soup of charged particles known as a plasma. This plasma is so incredibly diffuse that a single cubic meter of it might contain only a single atom. To put that in perspective, the air you are breathing right now has about 25 quintillion molecules in that same space. The WIM is, by earthly standards, an almost perfect vacuum. But it is a vacuum that stretches across billions of light years, weaving through the entire observable universe, and that sheer, unimaginable volume is the key. Even if each cubic meter holds just one lonely proton, when you add up all those cubic meters across the cosmic web, the total mass becomes staggering. This is why the WIM is the prime suspect. there is enough space out there filled with this faint, hot whisper of matter to potentially account for every single missing baryon. The problem is seeing it. A gas that hot and that thin is nearly invisible to the telescopes we have used for a century. It does not glow in visible light. It does not form stars. It hangs in the darkness between the glittering cities of galaxies, a ghostly infrastructure holding the universe together. So if we cannot see it with ordinary light, how do we prove it is really there? The hunt requires a different kind of detective, one that can see the universe in an entirely new spectrum. To find a ghost, you need to look for the shadow it casts. For the warm, hot intergalactic medium, that shadow is an almost imperceptible distortion in the oldest light in the universe. This is the third clue, a phenomenon known as the Sunyaev-Zeldovich effect. Think of the cosmic microwave background as a uniform, ancient wall of light, a backdrop that has been traveling to us for nearly 14 billion years. Now imagine a wisp of that superheated million-degree gas from the cosmic web. As photons from that ancient light pass through it, they do not go undisturbed. The incredibly energetic electrons in that hot plasma give the passing photons a tiny but measurable kick, scattering them to slightly higher energies. It is like shining a flashlight through a gentle haze of steam. The light does not get blocked, but its character is subtly changed. The result is a faint, cold spot imprinted on the cosmic microwave background in the direction of that hot gas cloud. This is not a shadow of darkness, but a shadow of a specific, predicted distortion. It is a fingerprint left on the primordial light by the very matter we are trying to find. Detecting this effect is one of the most delicate tasks in all of modern astronomy. It requires instruments of phenomenal sensitivity, often placed in the driest, highest deserts on Earth to avoid interference from water vapor in our own atmosphere. Giant telescope arrays like the Atacama Cosmology Telescope in the Chilean highlands scan the sky not for visible starlight, but for these minute variations in the microwave background. They are essentially mapping the universe's faintest pressure waves, the gentle pushes from electrons in hidden gas. When they combine these painstaking maps with observations of where galaxies are known to cluster, a ghostly image begins to develop. The distortions align perfectly with the predicted filaments of the cosmic web, tracing out the vast, invisible scaffolding that theory said must be there. Each one of those cold spots is a direct detection, a cosmic receipt proving that a massive reservoir of hot, diffuse matter exists exactly where we suspected. It is not a photograph of the gas itself, but a record of its interaction with the universe's oldest light. This clue transforms the whim from a compelling theoretical suspect into an entity we have actually measured. We are no longer just imagining the missing matter, we are beginning to see its silhouette. But seeing a silhouette is only half the proof. To truly identify our suspect, we need to analyze its chemical fingerprint. This brings us to the fourth clue, a method that reads the universe in a language of high-energy light. The warm, hot intergalactic medium, heated to millions of degrees, does not just distort background light. It also emits a faint, telltale glow of its own in the X-ray part of the spectrum. Think of a piece of metal in a blacksmith's forge. As it gets hotter, it first glows red, then yellow, then white. At millions of degrees, it would glow with X-rays, a light our eyes cannot see. The diffuse gas of the cosmic web is that superheated metal stretched across the cosmos. Its incredible temperature causes it to emit a whisper, soft X-ray signal. Catching that whisper is the work of space-based observatories like Chandra and XMM Newton. These are not optical telescopes. They are instruments designed to see the universe in X-rays, the signature of the most violent and energetic processes. They point their sensitive detectors at the vast, dark regions between galaxies, not looking for points of light, but for an extremely faint, diffuse haze. Finding this emission is like trying to see the heat shimmer above a desert highway from orbit. It is a monumental challenge, but in some of the densest knots of the cosmic web, where filaments intersect around massive galaxy clusters, these observatories have succeeded. They have detected that elusive, diffuse X-ray glow, confirming the presence of enormous reservoirs of million-degree gas precisely where the web's architecture predicts it should be. There is a second, even more powerful way to use X-rays as a detective tool. Instead of looking for the faint glow of the gas itself, we can use brilliant cosmic lighthouses shining from behind it. These are quasars, the intensely luminous cores of distant galaxies powered by supermassive black holes. Quasars are among the brightest X-ray sources in the universe. As that powerful beam of X-ray light travels across billions of light years to reach us, it passes through the invisible filaments of the warm, hot intergalactic medium. And just as sunlight passing through our atmosphere leaves a specific fingerprint of absorbed colors, the quasar's X-ray light gets imprinted with the signature of the hot gas. Atoms within the WIM, like oxygen and neon that have been stripped of most of their electrons by the intense heat, absorb very specific, precise amounts of energy from the quasar's beam. This creates dark lines in the quasar's otherwise smooth spectrum of X-ray light. Each line is a barcode identifying not only the presence of a specific element, but also its temperature, density, and distance. By analyzing these absorption lines, astronomers can do forensic chemistry on the cosmic web. They can confirm that the gas is there, measure how much of it there is, and even map its distribution along the line of sight to the quasar. It is a direct sampling of the universe's hidden infrastructure. Every time a mission like Chandra or XMM Newton catches a quasar spectrum with those characteristic absorption lines, it is like finding a water sample from a hidden underground river. It proves the river is real, tells us what is dissolved in it, and gives us a clue about its flow. Together, the faint emission and the sharp absorption lines provide the chemical evidence that places the WIM at the scene of the crime. We are moving from seeing its shadow to reading its identity card. But to solve the mystery completely, we need to know not just what the missing matter is, but where all of it is hiding. The map must be completed. There is another, even more brilliant cosmic flare that serves as the perfect probe. Fast radio bursts are among the most enigmatic and powerful signals in the universe. In less than the blink of an eye, these events release more energy than our sun does in 80 years. For a single millisecond, a source in a galaxy billions of light years away becomes a blindingly bright beacon across the cosmos. And while their ultimate cause remains a thrilling mystery, their journey to our telescopes provides a fifth, crucial clue to finding the missing matter. Every single one of these bursts is shaped by the space it travels through. As the flash races across the universe, it passes through the diffuse plasma of the cosmic web. This includes the warm, hot intergalactic medium, the very gas we are hunting. The free electrons in that plasma interact with the radio waves, causing a subtle but measurable delay. Lower frequency radio waves, like the deep notes of a song, get slowed down just a bit more than the higher frequencies. By the time the burst reaches Earth, this smear effect is recorded in its signal. Astronomers call this the dispersion measure. It is the total number of electrons the signal encountered along its entire billion light-year path. Think of it like a lighthouse shining through a thick cosmic fog. The thicker the fog, the more the light is scattered and delayed. A fast radio burst is that lighthouse, and the dispersion measure tells us exactly how much fog, how much diffuse ionized gas it had to travel through. When we detect a burst and pinpoint its home galaxy, we can calculate the distance. We then subtract the electrons we expect to find within that galaxy itself. The remainder, the vast majority of the signal delay, comes from the intergalactic medium itself. Each burst gives us a single, precise measurement of the total ordinary matter in the form of those spread-out electrons that exists between galaxies. It is a direct probe of the cosmic web's density. By collecting measurements from many bursts coming from different directions and distances, we are beginning to build a three-dimensional map of the universe's hidden baryons. The more bursts we detect, the clearer the picture becomes. Giant radio telescope arrays like the Canadian Hydrogen Intensity Mapping Experiment and the Deep Synoptic Array are now catching these fleeting signals by the dozens. Each new detection adds another data point, another strand of the cosmic web weighed and measured. These mysterious millisecond flashes, once just cosmic curiosities, have become one of our most powerful tools. They are not just messages from distant galaxies. They are diagnostics of the invisible ocean between them, confirming that the space we once thought of as empty is, in fact, teeming with the faint, hot residue of creation. But to understand why this matter ended up in these vast, thin filaments, we must rewind the clock. We need to understand the forces that sculpted the cosmic web in the first place. While fast radio bursts probe the hot, ionized plasma, there is another cosmic messenger that reveals a cooler, quieter component of the hidden universe. This clue comes from the beautiful and bizarre phenomenon known as the Lyman alpha forest. To understand it, we return to our brilliant cosmic lighthouses, the quasars. Their light does not just shine in X-rays, it blazes across the entire electromagnetic spectrum, including a powerful ultraviolet emission at a very specific wavelength called Lyman alpha. This is the fingerprint of neutral hydrogen, the most abundant element in the cosmos. As that torrent of ultraviolet light travels for billions of years to reach our telescopes, it does not travel through empty space. It passes through countless clouds and wisps of cooler hydrogen gas, floating in the vast expanses between galaxies. Each time the light encounters one of these clouds, the neutral hydrogen atoms within it greedily snatch a tiny, specific amount of energy from the beam. They absorb that characteristic Lyman alpha wavelength. Imagine a brilliant white light shining through a series of stained glass windows, each one a different shade of red. The light that finally emerges is missing specific red hues, creating a complex pattern. That is what happens to a quasar's light. When astronomers spread its light into a spectrum, they do not see a smooth rainbow. Instead, they see a stunning tapestry of hundreds, even thousands of sharp, dark absorption lines, all at slightly different wavelengths. This is the Lyman alpha forest. Each one of those dark lines is a shadow cast by a single cloud of intergalactic hydrogen. Because the universe is expanding, clouds at different distances are moving away from us at different speeds. This stretches the light, shifting the absorption line from its original position. The further away the cloud, the greater the redshift, and the more its shadow is shifted toward the red end of the spectrum. The result is a veritable forest of lines, each one marking the presence of a hydrogen cloud at a specific distance along the highway of light from the quasar to Earth. This forest is not random undergrowth, it is a direct map of the large-scale structure of the universe. The lines cluster in ways that trace the filaments and voids of the cosmic web, revealing where matter, even in this cooler, neutral form, is concentrated. While the warm, hot intergalactic medium is the superheated plasma, the Lyman alpha forest represents a cooler phase of the intergalactic medium, gas that has not yet been shock-heated to millions of degrees. It is the gentle mist before the forge. By studying the density and distribution of these lines, astronomers can take a census of this cooler baryonic matter. They can measure how much hydrogen is out there in these diffuse clouds and filaments. While individually each cloud is vanishingly thin, their collective sum across the entire observable universe adds up to a significant portion of the missing mass. The Lyman alpha forest is proof that the hidden baryons are not all in one single extreme state. They exist in a variety of temperatures and densities, from the cool, neutral clouds revealed by these ultraviolet shadows to the searing plasma detected by its X-ray glow. It shows us the full complexity of the cosmic web, a dynamic ecosystem of gas in different phases, all contributing to the grand total. But if this gas is spread so thinly across the cosmos, how did it get there in the first place? What cosmic forces could possibly take the raw material of creation and stretch it into such a vast, delicate web? Galaxies are not quiet islands, but engines of cosmic redistribution. Within their bustling stellar cities, two titanic forces act as great exporters of matter, launching vast quantities of baryons on a one-way trip into the void. The first is the spectacular death of massive stars. When a supernova explodes, it does not just create a beautiful nebula. It unleashes a shockwave of unimaginable power, a blast that can sweep up surrounding gas and hurl it out of the galaxy at speeds of thousands of kilometers per second. Imagine a volcanic eruption, but on a galactic scale, where the ash and debris are propelled so fiercely they escape the planet's gravity entirely. These stellar explosions create colossal bubbles and fountains of hot gas, rising above the galactic disk like a shimmering million-degree halo. The second force comes from the very heart of chaos. Supermassive black holes at the centers of galaxies, when they actively feed, become quasars. That process does not just produce light. It generates relativistic jets and intense radiation pressure that can push surrounding material outward with even greater ferocity than supernova. These active galactic nuclei can blow gigantic winds, clearing entire regions of a galaxy of their gas. Together, supernova and quasars act as cosmic bellows. They take baryons that were once neatly packaged into stars and cold gas clouds within a galaxy, and they heat them, ionize them, and violently eject them into the vast intergalactic wilderness. This is the delivery mechanism for the warm-hot intergalactic medium. Computer simulations of galaxy evolution paint a breathtaking picture of this process. They show vibrant, swirling galactic disks not as static portraits but as dynamic systems. From their surfaces, great geysers of color erupt, streams of blue and white representing cooler gas, and brilliant red and orange plumes depicting superheated material. These fountains rise, curl, and eventually fall back in some places, but in others they achieve escape velocity. They break free of the galaxy's gravitational grip entirely, becoming permanent contributions to the thin, hot plasma of the cosmic web. Every galaxy throughout cosmic time has been breathing out this enriched gas, with billions of galaxies each contributing their own exhaust over billions of years. It adds up to an immense reservoir. This clue solves a critical piece of the puzzle. It explains how the baryons got from the dense, luminous regions we can easily see into the diffuse, hidden realms we struggle to detect. They were not always missing, they were launched. The invisible architecture of the cosmos is far more than just empty space between galaxies. It is a dynamic, organized highway system where the missing matter flows. This structure, the cosmic web, is not built by the baryons themselves. It is sculpted by the gravitational pull of something far more mysterious, dark matter. Think of dark matter as the universe's unseen skeleton, a framework of immense mass that does not emit or absorb light. In the early universe, tiny fluctuations in density, imprinted by the Big Bang, grew under gravity's relentless pull. Regions with slightly more dark matter attracted more and more of it, while the spaces between them emptied out. Over billions of years, this process created a vast, three-dimensional lattice. Dense knots formed where filaments intersected, becoming the future homes of galaxy clusters. The long, thread-like strands connecting them are the filaments themselves. And it is within these filaments that the warm, hot intergalactic medium is concentrated. Why there? Gravity is the answer. As the universe evolved, ordinary matter, the baryons, fell into the gravitational wells created by the dark matter skeleton. Picture a network of gentle, cosmic valleys carved into the fabric of space. Gas naturally flows into these valleys, following the path of least resistance. But this journey is not a peaceful one. When streams of gas from different directions collide within a filament, they create immense shock waves. These shocks are like sonic booms on a cosmic scale, and they heat the gas to those staggering millions of degrees. The filament becomes a superheated pipeline, a river of plasma flowing toward the dense clusters at its intersections. This is why the missing baryons are not uniformly smeared across the void. They are channeled, concentrated along specific pathways. We can witness this breathtaking architecture through state-of-the-art computer simulations. Projects like Illustris TNG, which model the evolution of a vast cube of the universe, give us a time-lapse view of this process. In these visualizations, we do not see dark matter directly. Instead, we see its effects on the gas. The screen fills with a cosmic spiderweb of brilliant filaments, glowing in hues of orange, red, and white. The colors are a temperature map. The hottest gas, white and yellow, is found at the very hearts of the densest filaments and clusters where collisions are most violent. The cooler, redder gas traces the outer edges and quieter flows. Watching the simulation run is like seeing the universe breathe and grow. You witness galaxies forming at the knots, and you see vast plumes of gas ejected by supernova and black holes, joining and enriching the hot streams in the filaments. These simulations are not just pretty pictures. They are rigorous predictions that match the observational clues from the Sunyaev-Zeldovich effect and X-ray absorption. They show us that to find the missing baryons, we must look along the luminous threads of the cosmic web, the universe's hidden superhighways of hot gas. But if this web is so vast and filled with matter, why is it so difficult to see? What makes it the perfect hiding place? The very fabric of the universe carries an echo from its first moments, a whisper of sound frozen in time. This is the ninth clue, known as baryon acoustic oscillations. To understand it, we must journey back to the universe's infancy, just 380,000 years after the Big Bang. At that time, the cosmos was not a sea of stars and galaxies, but a seething, opaque plasma, a hot soup of particles and light. In that dense fluid, gravity was constantly trying to pull matter together into clumps. But it had a powerful adversary, radiation pressure from the intense light, which pushed everything apart. This created a tug of war, setting up a series of pressure waves that rippled outward through the primordial plasma. They were literal sound waves traveling through the early universe. Then, in an instant, everything changed. The universe expanded and cooled enough for atoms to form, allowing light to travel freely for the first time. That moment of release, the flash we see as the cosmic microwave background, also froze those sound waves in their tracks. Each wave had traveled a specific distance by that time, about 500 million light-years, creating a spherical shell of slightly denser matter around every initial seed. Think of dropping a pebble into a still pond. The ripple expands outward in a perfect circle. Now imagine that the pond instantly freezes solid at the exact moment the ripple reaches a certain distance. The frozen ripple is preserved forever. That is what happened on a cosmic scale. This frozen ripple, this standard distance, became a fundamental ruler etched into the structure of the cosmos. We see its imprint in two ways. First, in the distribution of galaxies themselves. When we create massive three-dimensional maps of millions of galaxies, like those from the Sloan Digital Sky Survey, we find a subtle statistical preference. Galaxies are slightly more likely to be separated by that specific frozen sound wave distance than any other. It is as if the universe has a preferred spacing, a faint memory of its own birth cry. But the second, and for our mystery more crucial, imprint is in the gas. That spherical shell of denser matter from the ancient sound wave was not just dark matter. It was also loaded with baryons, the ordinary atoms we are hunting. When galaxies eventually formed, they did so preferentially at the centers of those ancient seeds. But the baryonic shell, that frozen ripple, remained as a vast, diffuse halo of gas surrounding each galaxy cluster. This is a direct prediction. For every dense cluster of galaxies we see, there should be an enormous spherical reservoir of warmer, diffuse gas at a very specific distance from it, corresponding to that 500 million light-year sound horizon. This is not a guess, it is a fossil imprint from the universe's first 380,000 years. By using this standard ruler to measure the geometry of the universe, cosmologists can calculate the total density of all components, including ordinary matter. The measurements from galaxy surveys tightly constrain the number. They tell us with remarkable precision exactly how much baryonic mass the universe must contain today. That number, derived from the echo of primordial sound, matches perfectly the number from the cosmic microwave background. It is an independent, powerful confirmation that the missing baryons are not a myth or a miscalculation. They are a real, physical substance that must exist somewhere in the present day. The baryon acoustic oscillation is the universe's own measuring tape, and it tells us our inventory is correct. The atoms are out there. We just have to learn to see the ghostly halos they were frozen into so long ago. Our own galactic home holds a secret reservoir of its own. For decades, astronomers viewed galaxies as distinct islands of light, their edges defined by the last visible star. But we now know that every galaxy, including our Milky Way, is enveloped by a colossal, seething atmosphere of superheated gas. This is the circumgalactic medium, a halo of matter that extends for hundreds of thousands of light years, far beyond the sparkling spiral disk we see in photographs. If you could view the Milky Way in X-ray vision, the familiar band of stars would be a small, bright jewel at the center of a gigantic, shimmering cloud of million-degree plasma. This halo is not a static blanket. It is a dynamic interface, a cosmic battleground and recycling center. Here, gas blown out by supernova from within the galaxy mixes with pristine material falling in from the cosmic web. It is a perpetual cycle of fountain and rainfall, where atoms are heated, ejected, cooled, and eventually drawn back into fuel new generations of stars. For a long time, these enormous halos were virtually invisible. The gas is so hot it emits only a faint whisper of X-rays, and so diffuse that its light is drowned out by brighter sources. Its discovery required a clever trick. Instead of trying to see the halo of our own galaxy directly, which is difficult from our position inside it, astronomers looked at distant, bright quasars. As the light from these beacons passed through the halos of foreground galaxies on its way to Earth, it provided a perfect backlight. By analyzing the specific absorption lines imprinted on the quasar's spectrum, scientists could detect the signature of oxygen, neon, and other elements that had been stripped of electrons by the intense heat. This forensic work revealed that these galactic halos contain staggering amounts of material. The circumgalactic medium around a single large galaxy can hold as much mass as all the stars within that galaxy itself. Think of it this way: the visible galaxy is just the tip of a vast, hot iceberg. For every ton of matter we see shining as stars, there is another ton of matter floating invisibly in this extended, gaseous atmosphere. Composite images tell the story powerfully. A standard optical photo shows a beautiful spiral galaxy, a disk of stars against the black of space. But when you layer on data from X-ray observatories, the galaxy is suddenly engulfed in a brilliant, colorful haze. Blues and purples might show cooler, accreted gas, while fiery reds and yellows trace the superheated outflows from stellar explosions. This halo is a crucial piece of the missing baryon puzzle. While the warm, hot intergalactic medium fills the vast filaments between galaxies, these circumgalactic halos represent the local storage units, the immediate surroundings of each galactic city. They are a significant reservoir of ordinary matter that was hiding in plain sight, simply because we were not looking in the right light. The universe is not made of isolated islands. It is made of islands shrouded in massive, energetic fog banks, and we are only just beginning to map their true extent. But if galaxies are constantly breathing this gas in and out, what happens to it over the eons? Does it ever truly escape, or is it all destined to fall back home? The most massive structures in the universe, however, tell a very different story. Galaxy clusters are the titans of the cosmos, colossal cities of hundreds or even thousands of galaxies bound together by gravity. They are not just collections of stars. They are filled with an immense ocean of superheated gas known as the intracluster medium. This gas is so incredibly hot, tens of millions of degrees, that it shines brightly in X-rays. When telescopes like Chandra point at a cluster such as the famous Coma cluster, they see a spectacular glowing cloud of plasma that utterly dwarfs the individual galaxies within it. This fiery halo is the single largest reservoir of ordinary matter in the local universe that we can directly observe. And here is the crucial point. When astronomers weigh this brilliant, hot gas, they find it accounts for a stunning amount of the cluster's total baryonic content. In fact, within the boundaries of these massive clusters, the ratio of hot gas to stars aligns almost perfectly with the cosmic predictions from the microwave background. Inside these gravitational fortresses, the baryon budget appears balanced. The atoms are all present and accounted for. This discovery is a vital clue because it tells us the missing matter is not hiding within the densest knots of the cosmic web. The problem is not local. The clusters have held onto their share of the primordial material. The discrepancy must therefore exist on the larger, more diffuse scales between these clusters in the vast filamentary highways and the lonely voids. The clusters are like oases in a desert, places where the water has pooled and is easy to see. The mystery lies in the parched stretches between them, where the water exists only as a thin, elusive vapor. This focus shifts the search away from the bright, obvious cities and into the dark, connecting countryside of the cosmos. If the clusters have their full allotment, then the missing half must be spread across the unimaginable volumes of space that separate them. But within these brilliant, hot clusters lies a paradox that challenges our understanding. At the very heart of many massive clusters, X-ray telescopes reveal something unexpected. A core of gas that is significantly cooler and denser than the surrounding inferno. According to the simplest physics, this is a recipe for disaster. In such a dense environment, the hot gas should be radiating away its energy as X-rays at a ferocious rate. As it cools, it should contract, flowing inward in a torrential, cooling flow to the cluster's center. There, with nothing to stop it, this vast river of cold gas should collapse into a frenzy of new star formation, birthing thousands of stars every year. The central galaxy should be the site of a spectacular stellar baby boom. Yet when astronomers look, they see nothing of the sort. The predicted deluge of star formation is missing. The gas cools, but it does not collapse. It is as if a boiling pot of water was suddenly, mysteriously kept from turning into ice, defying every expectation. This is the cooling flow problem, and it points to a hidden source of energy, a cosmic thermostat preventing the catastrophic chill. The leading suspect is once again the supermassive black hole at the cluster's central galaxy. When gas does begin to cool and flow inward, some of it inevitably feeds the black hole. This does not happen quietly. The black hole responds by unleashing titanic jets of relativistic particles and intense radiation, a process known as active galactic nucleus feedback. These jets blast back into the surrounding hot gas like cosmic blowtorches, injecting just enough energy to reheat the cooling core, stirring the pot and preventing the runaway cooling. In spectacular X-ray images, we can see the evidence of this battle. The brilliant, smooth glow of the hot intracluster medium is punctuated by vast, dark cavities bubbles carved out by the black hole's jets. These bubbles, which can be hundreds of thousands of light years across, push the hot gas aside, creating ripples and shock waves that distribute the energy throughout the core. It is a finely balanced feedback loop. Cooling gas triggers black hole activity, which heats the gas and suppresses further cooling. This process is crucial for our baryon hunt because it tells us that the hot gas in clusters is not a passive reservoir. It is a dynamic, actively managed system. Energy is constantly being recycled and redistributed, which affects how we measure its total mass and temperature. If we misunderstand this balance, we could miscalculate the baryon content of these giant structures. The cool core puzzle reminds us that the hidden matter of the universe is not sitting still. It is part of a living, breathing ecosystem where gravity, radiation, and black hole fury are in a constant, delicate dance, ensuring that the cosmic ledger remains far more interesting than a simple list of numbers. While the giants of the cosmos command our attention, the true population of the universe whispers in the faintest of lights. Dwarf galaxies are the cosmic multitude, small, faint stellar systems that outnumber their larger spiral and elliptical cousins by a staggering margin. Our own Milky Way is orbited by dozens of these dim satellites, and they are thought to swarm around every large galaxy in the universe. Their significance in the Missing Baryon mystery lies not in their visible stars, which are few, but in what surrounds them. Each of these countless dwarfs is likely enveloped by its own extended halo of gas, a circumgalactic medium on a smaller but far more numerous scale. Imagine a giant sequoia tree in a forest. It has a vast root system and a broad canopy. Now imagine thousands of small shrubs surrounding it. Each shrub has its own tiny, shallow root system. But if you add up the total area covered by all those small root networks, they could easily surpass the reach of the single giant tree. Dwarf galaxies, in their sheer abundance, may collectively possess an enormous reservoir of diffuse, hot gas in their halos. This gas is exceptionally difficult to detect. The galaxies themselves are so faint that their starlight barely registers. The surrounding halo gas, even hotter and more diffuse than in large galaxies, emits an X-ray whisper too soft for most telescopes to distinguish from the background hum of the universe. We see hints of this in simulations. When cosmologists run models of cosmic structure formation, they show every dwarf galaxy, even the tiniest, sitting within a fuzzy cocoon of dark matter and a shroud of baryonic gas. These halos are not isolated. They overlap and intertwine, especially in the dense environments around large galaxies, potentially creating a continuous, frothy medium of warm gas that fills the spaces between all galaxies, big and small. Could this collective fog from a trillion faint dwarfs account for a meaningful slice of the missing baryons? It is a compelling possibility. The challenge is moving from simulation to confirmation. Detecting this gas requires observing these galaxies not in visible light, but in the far ultraviolet and soft X-ray bands, and often requires stacking data from many dwarfs to build up a signal from the statistical noise. It is detective work of the most painstaking kind, searching for the breath of ghosts. Yet if this pervasive, low-density gas exists, it represents a hidden dimension of the cosmic web, a fine mist clinging to every thread and knot, adding its silent weight to the universe's hidden ledger. Our own night sky holds a faint, pervasive glow that has nothing to do with stars. If your eyes could see in X-rays, the entire celestial sphere would shimmer with a soft, diffuse light, a cosmic fog enveloping our solar neighborhood. This is the diffuse galactic emission, a whisper of high-energy light emanating from the hot gas of our Milky Way's vast halo and the local filaments of the cosmic web we are embedded within. It is the warm, hot intergalactic medium, but seen from the inside, a clue hiding in our own galactic backyard. For decades, this faint emission was just a blurry background, a nuisance signal astronomers had to subtract to see brighter, more distant objects. But now, with instruments of exquisite sensitivity, that blur has become the target. The key to mapping this fog is a space-based observatory called EROSITA. This remarkable X-ray telescope, mounted on the Russian-German Spectre RG spacecraft, performed an unprecedented all-sky survey. It did not just look at specific points. It slowly scanned the entire heavens, meticulously measuring the X-ray brightness of every single patch of sky. The resulting map is breathtaking. It shows the Milky Way not as a band of stars, but as a colossal, bubbling cauldron of hot gas. Vast, faint structures arc across the map in hues of red and gold, tracing the outlines of million-degree bubbles blown by ancient supernova and the gentle, pervasive glow of the circumgalactic medium. One of the most stunning revelations is the sheer scale of this emission. It is not confined to the galactic disk. It extends far above and below the plane of the Milky Way, confirming that our galaxy is sitting in the middle of an immense, hot atmosphere hundreds of thousands of light years across. This local halo is not a smooth, uniform blanket. The EROSIT map reveals intricate details, tendrils, loops, and cavities. Some features are the ghosts of individual stellar explosions from millions of years ago. Others appear to be the imprint of our galaxy's violent past, collisions with smaller galaxies that stirred the hot gas like a spoon in a cup of tea. And still others may be our closest direct view of the cosmic web itself, where the Milky Way's own halo gas blends seamlessly into the warmer, more diffuse filaments of the intergalactic medium. This diffuse glow is more than just a pretty picture. By analyzing its spectrum, the precise energy signature of the X-ray light, scientists can determine the temperature, density, and chemical composition of this hot plasma. They can ask, is this gas primarily the exhaust from our galaxy's own star formation, or is it primordial material, the ancient baryons that have been part of the cosmic web since the beginning? The answer is likely a complex mixture of both. Our local fog is a galactic recycling center and a cosmic reservoir combined. Missions like EROSIT transform this faint background from noise into a critical data set. Every photon in that all-sky map is a messenger from the hottest, most elusive matter in our vicinity. It proves that the missing baryons are not just a distant abstraction concerning far-off quasars and galaxy clusters. They are here, surrounding our own stellar island, a faint but omnipresent haze we are only now learning to read. If our own galactic neighborhood is this filled with hidden, hot gas, what does that imply for the truly empty reaches of space, the great voids between the web's filaments? Magnetic fields are the universe's invisible artists, painting lines of force across the void. We often think of them surrounding planets or stars, but they also permeate the deepest intergalactic space, woven through the very filaments of the cosmic web. These fields are unimaginably weak, billions of times fainter than a common refrigerator magnet, yet across distances of millions of light years, their influence can be profound. For the warm, hot intergalactic medium, this subtle force could be a key player. The magnetic field lines, like an ethereal scaffolding, could help confine the searing plasma within the filaments, preventing it from dissipating even further into the emptiness of the cosmic voids. They might also play a role in heating the gas itself, as the turbulent motions of plasma stretching and twisting these field lines convert energy into heat, like rubbing your hands together to generate warmth. This magnetic confinement and heating would directly affect how the WIM behaves and, crucially, how we are able to detect it. The absorption lines we see in quasar spectra, the faint X-ray glow, even the dispersion of fast radio bursts, all these signals could be subtly shaped by the presence of these vast, invisible magnetic structures. The challenge is measuring something so faint. We cannot simply put a magnetometer in intergalactic space. Instead, astronomers rely on indirect and ingenious methods. One technique involves studying the polarization of light from distant radio galaxies. As this light travels through magnetized regions of the cosmic web, its polarization can rotate, a phenomenon known as Faraday rotation. The amount of rotation tells us about the strength and direction of the magnetic fields along the line of sight. Another method looks for synchrotron radiation, the faint glow emitted by electrons spiraling around magnetic field lines at nearly the speed of light. In visualizations of the cosmic web, we might see these magnetic fields depicted as delicate blue or white threads, tracing along the fiery orange filaments of hot gas. They are the fine silk woven into the universe's grand tapestry, a subtle but essential component that may be holding the missing matter in place and dictating its final, elusive form. The universe's first dawn was not a gentle sunrise but a cosmic wildfire. Long before the majestic spirals and clusters we see today, the cosmos was a dark, neutral sea of hydrogen and helium. Then something changed. The first stars ignited, monstrous behemoths 100 times the mass of our sun, blazing with a ferocious ultraviolet light. Their birth marked the beginning of the reionization era, a fundamental transition that may hold a direct clue to the state of the missing baryons. When those first brilliant stars and early quasars switched on, their intense radiation acted like a universal blowtorch. It ripped electrons from the atoms of the surrounding pristine gas, transforming the cool, neutral fog that filled the universe into a hot, ionized plasma. This was not a local event. Over hundreds of millions of years, bubbles of ionized gas grew around every luminous source, eventually overlapping until the entire intergalactic medium was transformed. This process permanently changed the nature of cosmic matter. The energy injected during reionization did not just light up the darkness. It provided the initial, monumental heating event that could have sent vast quantities of baryons on their journey into the diffuse state we now call the warm-hot intergalactic medium. Artistic depictions of this era are hauntingly beautiful. They show a dark cosmos pierced by islands of searing blue and white light, the first stellar nurseries. Radiant tendrils and shock fronts expand from these points, carving out vast, irregular bubbles in the murk. Inside these bubbles, the gas is no longer a cool, placid pool, but a shimmering, energetic plasma. This is the universe's formative trauma, the moment its basic ingredients were fundamentally altered. The heat from reionization gave the baryons a powerful kick, making them more resistant to collapsing back into the densest dark matter halos. It set them on a path to remain in a more spread-out, energetic state, floating in the vast intergalactic volumes rather than settling neatly into galaxies. In a very real sense, the search for the missing baryons is a search for the aftermath of this first cosmic dawn. We are looking for the material that was heated, ionized, and scattered by the very first light in creation, a fossil record of the universe's awakening. If the energy of reionization is what initially dispersed these atoms, then the modern cosmic web is the legacy of that ancient fire, a structure built from material that has been hot and diffuse for almost the entire history of time. That faint shadow on the cosmic microwave background has a hidden twin. The Sunyaev-Zeldovich effect we discussed earlier is technically the thermal version, caused by the random, frantic motions of electrons in the hot gas giving photons a kick. But there is another, even more subtle signature known as the kinetic Sunyaev-Zeldovich effect. This one is not about temperature, it is about motion. Imagine standing still in a gentle rain and the raindrops fall straight down on you. Now imagine you start running forward. From your perspective, the raindrops are no longer falling vertically. They are coming at you at a slight angle, hitting you a bit harder on your front. This shift in perception is like a Doppler effect for rain. The kinetic SZ effect is the cosmic version of this. It occurs when an entire cloud of that million-degree gas in the cosmic web is itself in motion, streaming along a filament or falling into a galaxy cluster. As the photons from the cosmic microwave background pass through this moving cloud, they are not just given a random thermal kick. They are also systematically shifted because the cloud itself is moving. If the cloud is moving toward us, the scattered photons get a tiny blue shift. If it is moving away, they get a red shift. The resulting imprint on the microwave background is an even fainter, more specific distortion. A patch of sky that appears minutely warmer or cooler not because of the gas's heat, but because of its bulk flow through the universe. Detecting this signal is one of the most formidable challenges in observational cosmology. It is like trying to hear a single instrument tuning within a symphony while you are standing a mile away from the concert hall. The thermal SZ effect is the loud symphony. The kinetic effect is that one soft, precise note. To find it, astronomers must combine exquisitely sensitive maps of the cosmic microwave background, like those from the Planck satellite, with independent measurements of where the gas is and how it should be moving based on the gravitational pull of the surrounding dark matter web. When they can isolate it, the payoff is extraordinary. The kinetic Sunyaev-Zeldovich effect does not just tell us the hot gas is there, it tells us where it is going. It allows us to map not just the structure but the dynamics of the cosmic web. We can see the rivers of plasma flowing toward the great clusters, tracing the gravitational currents of the universe in real time. In a theoretical diagram, you might see two side-by-side images of a galaxy cluster. The first, labeled thermal SZ, shows a simple, smooth halo of distortion. The second, labeled kinetic SZ, reveals a more complex pattern, with red and blue hues indicating motion toward and away from us, showing the gas swirling and accreting in a vast cosmic whirlpool. This clue moves us from a static snapshot of the missing baryons to a living movie. It confirms that the warm-hot intergalactic medium is not a placid fog, but an active participant in the cosmic dance, pulled by gravity and flowing along the dark matter highways. By reading its motion, we learn not only where the missing atoms are, but what they are doing, bringing us one step closer to understanding the full, dynamic life cycle of the universe's ordinary matter. Every fingerprint tells a story, and the universe's hidden gas leaves one of the most specific. The story of the missing baryons is written in the ghostly signatures of oxygen atoms that have endured a cosmic inferno. In the searing heat of the warm, hot intergalactic medium, atoms are not just stripped of 1 or 2 electrons, they are brutally assaulted, losing 6, 7, or even 8 of their electrons. An oxygen atom normally has 8. When it loses 7, it becomes what scientists call O-8, a single, lonely electron orbiting a massive, positively charged nucleus. When it loses 6, it becomes O-7. These are not stable states you find on Earth. They are the marks of matter pushed to an extreme, and they absorb very precise, telltale amounts of energy. When the brilliant X-ray light from a distant quasar passes through a filament of this hot gas, these maimed oxygen atoms reach out and steal only the exact energy that matches their own tortured configuration. This leaves a dark, narrow line in the quasar's spectrum at a very specific wavelength. Finding that line is like finding a single, perfect needle in a haystack the size of a continent. The work begins with observatories like Chandra, which must stare at a single, carefully chosen quasar for days, sometimes even weeks, collecting enough X-ray photons to build a usable spectrum. The raw data is a faint, sputtering trickle of numbers. Scientists then process this data, smoothing out the noise and plotting the intensity of the light against its energy. What they hope to see is not a dramatic spike, but a subtle dip. On a graph, the spectrum appears as a generally smooth, sloping line. But if you zoom in, right at the precise energy corresponding to O-7 or O-8, you might see the line dip downward just a fraction. It is a tiny, almost hesitant indentation in the data. In a published scientific figure, this feature is often highlighted with a vertical dashed line and a small arrow, pointing to that faint trough with the label O-7 or O-8. It looks insignificant, a mere wiggle on a plot, but that wiggle is a direct detection. It is a chemical analysis performed across 1 billion light-years. Each one of those dips confirms the presence of million-degree gas, measures its density, and even tells us how fast the filament is moving toward or away from us based on the slight shift of the line's position. It is the smoking gun. While the Sunyaev-Zeldovich effect shows us the silhouette of the hot gas, these oxygen absorption lines let us taste it, analyze its temperature and composition. They transform a theoretical suspect into a chemically identified entity. Every time astronomers confirm one of these lines, they are essentially catching a sample of the missing universe in a test tube made of light, proving that the atoms are not just out there, but that they bear the exact scars of the cosmic web's fiery embrace. But the universe left us a second, even earlier receipt. Before the cosmic microwave background, before the first stars, even before atoms were fully formed, there was a brief, explosive period of nuclear fusion. In the first 3 minutes after the Big Bang, the entire cosmos was a seething nuclear furnace, hot and dense enough for protons and neutrons to collide and stick together. This epoch, known as Big Bang nucleosynthesis, forged the very first atomic nuclei from the primordial soup. It produced vast amounts of helium-4, along with tiny, precious traces of other light elements, deuterium, helium-3, and lithium-7. The crucial fact is this: the recipe for this primordial fusion was exquisitely sensitive to one ingredient, the density of protons and neutrons, the baryons. A denser early universe would have burned nearly all the deuterium into helium. A thinner one would have left more deuterium behind. The final abundances are a direct, permanent record of the baryon density when the universe was just 100 seconds old. Think of it as a cosmic fossil from the first moments of creation. Astronomers have spent decades measuring the pristine abundances of these light elements in the oldest places they can find, in distant, nearly unevolved gas clouds and in the outer regions of ancient stars. The amount of deuterium they find, in particular, is a fantastically precise baryometer. When they plug that number into the equations, it gives them a figure for the total density of ordinary matter in the cosmos. And this number, derived from the first 3 minutes of time, matches with stunning precision the number later etched into the cosmic microwave background at 380,000 years. Two completely independent probes, one from nuclear physics and one from the relic light of recombination, agree perfectly on the universe's starting inventory of normal stuff. This is our foundational clue, the anchor point for the entire mystery. The baryons we are hunting for are not a theoretical fantasy. They are a quantity mandated by the universe's own first nuclear reactions, a number written into the oldest chemistry of existence. Every attempt to solve the missing baryon problem must ultimately bring half of this specific primordial mass back into the ledger. These predictions, however, are only as good as our ability to test them against reality. The 20th clue in our mystery is the delicate, ongoing dance between simulation and observation. Supercomputer models like Illustris and EAGLE have given us a breathtaking theoretical vision of the cosmic web, showing exactly where the missing baryon should be flowing. But the universe does not always follow our most elegant code. Placing a simulated image side by side with an actual observational map reveals both profound successes and stubborn gaps. In one compelling comparison, we see two depictions of the large-scale structure of the universe. On one side, the simulation, a stunning, high-resolution web of golden filaments against a dark blue void, with dense, white knots marking galaxy clusters. The structure is crisp, continuous, and complete, a perfect cosmic blueprint generated by the laws of physics as we understand them. On the other side, an observational map built from thousands of galaxy positions or from the subtle imprints of the Sunyaev-Zeldovich effect. This map is noisier, grainier. The filaments are not smooth rivers of light, but broken chains of faint dots and blurred smudges. The voids are not perfectly empty, but speckled with uncertain data points. The overall architecture matches beautifully. The simulated web and the observed web share the same skeleton. This is a monumental success, proving our core understanding of gravity and cosmic evolution is correct. The simulations predicted the web and we found it, but the devil and the missing baryons are in the details. The simulations tell us precisely how much gas should be in each filament, at what temperature and in what state. When we point our real telescopes at those same filaments, we often measure less. The observed X-ray glow is fainter. The absorption lines in quasar spectra are weaker. The census still comes up short. This discrepancy is not a failure, it is a guide. It tells the observers where to look harder and with better instruments. It tells the simulators that they might be missing a piece of physics, perhaps the way energy from black holes or supernova disperses the gas even more effectively than modeled, puffing it up to densities too low for our current tools to see. This back and forth is the scientific method operating on a cosmic scale. The simulations provide the treasure map, and the observations are the grueling, ground-level search. Each new, deeper observation that finds a bit more of the predicted gas validates the map. Each persistent shortfall forces a redrawing of the lines. This iterative process is how we close the gap, pixel by pixel, until the simulated universe and the real one finally align, revealing the last hiding places of the atoms that built everything. Our cosmic treasure map is only as good as the instruments we use to read it. For decades, we have been squinting at the faint signatures of the missing baryons, straining to see details in the noisy glow. The next great leap in this hunt is already on the horizon, embodied by two revolutionary space telescopes. The first is XRISM, a joint mission by JAXA and NASA. Its name stands for X-ray Imaging and Spectroscopy Mission, and its power lies in a single, extraordinary instrument called Resolve. This is a microcalorimeter spectrometer, a device so sensitive it can measure the energy of individual X-ray photons with a precision never before achieved. Think of the current absorption lines we see in quasar spectra as blurry, pixelated smudges. XRISM will transform those smudges into razor-sharp, high-definition barcodes. With this clarity, astronomers will not just detect the presence of hot oxygen in a filament. They will be able to measure its exact temperature, density, and velocity with unprecedented accuracy, mapping the complex motions and conditions within the warm-hot intergalactic medium for the very first time. It is like moving from a grayscale sketch to a full-color, three-dimensional model. Artist concepts show XRISM as a sleek, silver observatory with a long telescope tube gliding silently against the blackness of space, its solar panels outstretched like wings. It represents a new era of precision chemistry performed across the cosmos. But to solve a mystery this vast, we need more than precision. We need sheer, overwhelming coverage. That is the promise of Athena, the Advanced Telescope for High-Energy Astrophysics, a flagship mission being developed by the European Space Agency. Where XRISM is a precision scalpel, Athena is a wide-angle floodlight combined with a powerful microscope. It will carry the largest X-ray mirror ever built and instruments capable of both wide-field imaging and exquisite spectroscopy. Athena's true power is in its survey capability. It will perform deep, sweeping scans of the sky, not just looking at a few pre-selected quasars, but mapping the X-ray universe in its entirety. It will detect millions of active black holes and, in the spaces between them, build a statistical map of the diffuse cosmic web's emission and absorption unlike anything we have today. In stunning artist illustrations, Athena appears monumental, a complex structure of golden foil mirrors and intricate instrumentation, poised to capture the high-energy heartbeat of the entire universe. Together, XRISM and Athena represent the future of this detective story. One will give us intimate, detailed portraits of the missing matter's chemistry. The other will provide the grand, contextual map showing how it all fits together. They are the tools being forged now to finally, conclusively, close the case on the universe's greatest inventory mystery. Radio astronomy holds the key to a three-dimensional map of the missing universe. While space-based telescopes peer at X-rays, a new generation of colossal ground-based arrays is being built to listen. Their target is the chorus of fast radio bursts, those fleeting cosmic flashes that act as perfect probes of the intergalactic fog. The next chapter in this hunt will be written by two monumental projects, the Square Kilometre Array and the Next Generation Very Large Array. These are not single telescopes, but vast networks of antennas spread across continents, working in unison to capture the faintest whispers from the cosmos. The Square Kilometre Array, or SKA, will be the largest radio observatory ever constructed. Its core will sprawl across remote regions of South Africa and Western Australia, with thousands of dish antennas and even more simple dipole receptors stretching for hundreds of miles. Its design is almost organic, like a field of metallic flowers or a vast technological forest growing from the desert floor. The Next Generation Very Large Array, or NGVLA, will transform the iconic Y-shaped array in New Mexico into a system 10 times more powerful, with new stations stretching across North America. Their combined power is difficult to overstate. Where current telescopes might catch a few dozen fast radio bursts per year, these future giants will detect them by the thousands, perhaps even tens of thousands. Every single one of those millisecond bursts is a diagnostic tool. As each flash travels billions of light years to reach us, its dispersion measure. The smear caused by electrons in the cosmic web provides a direct measurement of the total ordinary matter along its path. With thousands of bursts pinpointed to distant host galaxies, astronomers will no longer be taking sparse, individual measurements. They will be building a dense, three-dimensional point cloud of the universe. Imagine a dark room representing the cosmos. Today, we have a handful of flashlight beams cutting through the darkness, each showing a thin column of floating dust. The SKA and NGVLA will switch on 10,000 flashlights all at once from every possible angle. Suddenly, the entire volume of the room is illuminated, revealing the intricate swirls and densities of the dust cloud in full, breathtaking detail. This is the promise, a three-dimensional tomographic map of the warm-hot intergalactic medium across cosmic time. We will see how the filaments of hot gas thicken and evolve, how they connect galaxy clusters, and how much mass they truly contain. By statistically analyzing the dispersion from bursts at different distances, scientists will be able to weigh the cosmic web directly, filament by filament, void by void. These radio arrays will do more than just count bursts. Their incredible sensitivity and resolution will allow them to study the immediate environments where bursts are born, potentially solving that mystery too. And by linking with optical and X-ray telescopes, they will create a multi-messenger portrait of the universe where a single fast radio burst's journey is analyzed in radio, its host galaxy studied in visible light, and the predicted hot gas along its path scrutinized in X-rays. The silent deserts and plains chosen for these sites will become portals to the hidden architecture of everything. When they finally listen, they will hear the universe's missing matter speaking through the delayed echoes of cataclysmic events, finally completing a census begun with the first light of creation. The invisible hand guiding this cosmic architecture is not made of atoms. Dark matter, that mysterious substance that outweighs normal matter by a factor of 5, does more than just sculpt the web. It may hold the ultimate key to where the missing baryons have settled. For decades, we have thought of dark matter as a ghostly presence, interacting with our world only through the gentle, persistent pull of gravity. But what if there is more to the story? Some radical theories suggest dark matter and ordinary matter might share a subtler, more complex relationship, a faint whisper of interaction beyond gravity that could have profound consequences for our search. One provocative idea is the concept of dark baryons. This is not a new type of particle, but ordinary protons and neutrons that have been rendered invisible by an exotic process. Could some of the missing baryons have been transformed or hidden within the deep gravitational wells of dark matter halos in a way our telescopes cannot yet perceive? The standard model says dark matter is collisionless. Particles of dark matter pass right through each other like ghosts. But if dark matter particles could interact with each other even slightly, or with baryons through some unknown force, it would change everything about how structures form. It could slow down the collapse of gas into galaxies, or it could heat the baryonic gas through friction, puffing it up into even more diffuse, hotter states that are even harder to detect. Visualize a supercomputer simulation side by side. On one side, a model with simple, gravity-only dark matter shows galaxies forming within smooth, spherical halos with gas flowing in along predictable filaments. On the other side, a model with interacting dark matter reveals a strikingly different cosmic web. The dark matter halos themselves might be smoother, less concentrated, and the gas within them is stirred, warmer, and more spread out. The ordinary matter is not missing, it is there, but its distribution has been fundamentally altered by its dance with the unseen partner. This connection forces us to ask a deeper question. Is the Missing Baryon problem truly a problem of detection, or is it a clue pointing to a flaw in our understanding of the dark universe itself? Perhaps the baryons are exactly where our gravity-based models predict, but in a form so thoroughly mixed with or influenced by the dark matter that we have been looking for the wrong signature. Each filament of the cosmic web is a double helix, one strand of dark matter gravity and one strand of hot, ionized gas, twisted together by the history of the universe. Finding one may require us to fully understand the other. The most radical solution to this mystery does not hide the missing atoms but destroys them entirely. Could a significant portion of the universe's original baryons have been crushed out of existence in the first fraction of a second after the Big Bang, collapsing directly into swarms of tiny, ancient black holes? This is the provocative idea of primordial black holes, and it represents a truly exotic alternative to the cosmic web theory. Unlike the stellar black holes we know, formed from the collapse of massive stars, primordial black holes would have been forged from the intense density fluctuations in the newborn cosmos. In those first chaotic moments, patches of space that were slightly denser than average could have undergone gravitational collapse so complete that they punched a hole right through the fabric of space-time. The result would be a universe seeded not just with particles, but with countless invisible gravitational knots, ranging in size from smaller than an atom to as massive as a planet. Visualize this not as a structured web, but as a dark, churning swarm. Artistic depictions show a deep space backdrop peppered not with stars, but with millions of tiny, perfectly black spheres, each one a gravitational singularity, warping the light around them into faint, shimmering halos. They would be everywhere, undetectable by the light they absorb, only hinted at by their subtle gravitational effects. If enough of these primordial black holes were created, they could, in theory, account for the missing baryonic mass. The atoms would not be floating in hot filaments. They would be locked away forever behind event horizons, removed from the cosmic ledger of observable matter. So why is this considered a long shot? The constraints are severe. Such a population of black holes would leave specific imprints on the cosmos that we have not seen. They would distort the light from distant stars through a phenomenon called microlensing, creating predictable flickers that large surveys have largely failed to find in the necessary numbers. They would affect the precise way galaxies clump together, and they would inject energy into the early universe in ways that might conflict with our measurements of the cosmic microwave background. Each of these non-detections closes another window of possibility, limiting how much of the missing mass could possibly be hiding in this form, yet they are not entirely ruled out. A small population or black holes within a very specific mass range could still be lurking, contributing a sliver to the mystery. This idea serves as a vital reminder. In a detective story of this scale, every possibility, no matter how strange, must be examined and tested against the evidence. The enduring appeal of the primordial black hole theory is not that it is likely, but that it forces us to question our most fundamental assumptions about what matter is, and what forms it can ultimately take when the universe itself is the forge. Solving this mystery is about more than just finding lost atoms. It is about completing the most fundamental inventory of all, the census of tangible reality. For centuries, we have looked up at the night sky and wondered what it is made of. We have built telescopes to see further and particle colliders to probe deeper, all to answer a simple, profound question: what is everything? The Missing Baryon Problem is the final ledger entry in that cosmic accounting. When we finally confirm where every last proton and neutron resides, we will have done something extraordinary. We will have taken a universe born from a hot, dense state nearly 14 billion years ago, tracked its expansion, its structure formation, and the intricate dance of its components, and shown that our story of it is complete. The equations we scribbled on blackboards, the supercomputer simulations that spun out virtual universes, the grand theoretical framework of the Big Bang and cosmic evolution, all of it hinges on this simple physical check. Did we count everything correctly? Finding the missing half of normal matter is the ultimate audit. A successful audit does not just balance the books. It validates the entire enterprise of cosmology. It tells us that our understanding of gravity, of nuclear physics in the first 3 minutes, of the growth of structure from tiny seeds is essentially correct. The universe, in its deepest workings, is comprehensible. This is a humbling and awe-inspiring realization. We are fleeting creatures on a tiny rock, using mathematics and ingenuity to trace the history and distribution of the very stuff that formed us across distances and timescales that dwarf human imagination. And the story checks out. Visualize a slow, majestic pan across the cosmic web in its full, simulated glory, the brilliant golden filaments against the deep black void, the dense clusters glowing like cities. Then overlay the observational data, the pinpoints of fast radio bursts, the faint X-ray halos, the subtle shadows on the microwave background. Watch as they align perfectly with the predicted structure. The map and the territory become one. The philosophical weight of this is immense. It means the normal matter, the atoms in our bodies, the iron in our blood, the silicon in our planet, is not some rare anomaly. It is part of a vast, continuous flow, a cycle that stretches from the first stars to the distant future. The oxygen we breathe was forged in stellar furnaces, ejected into the cosmic web, and later gathered to form our solar system. We are literally made of the universe, and now we are mapping its full anatomy. To solve this problem is to connect ourselves physically and intellectually to the grand architecture of everything. It confirms that we belong to this cosmos, not just as inhabitants, but as its conscious cartographers. The final clue is not a location on a map, but a quiet confidence that we are learning to read the universe's story and finding our own place written within it. The final pieces of this cosmic puzzle are now falling into place. From the ancient whisper of the cosmic microwave background that gave us the original inventory, to the ghostly silhouette of the warm, hot intergalactic medium revealed by the Sunyaev-Zeldovich effect, each clue has built upon the last. We followed the chemical fingerprints in X-ray absorption lines, the delayed whispers of fast radio bursts, and the intricate map of the Lyman alpha forest. We saw how supernova and black holes act as cosmic bellows, ejecting matter into the web, and how the dark matter skeleton sculpts the rivers where this hot plasma flows. We discovered vast reservoirs in galactic halos and cluster cores, confronted the cooling flow paradox, and considered the collective fog of dwarf galaxies. The faint glow in our own backyard from missions like EROSITA, the subtle influence of magnetic fields, the lasting echo of reionization, and the dynamic hint of the kinetic SZ effect all added crucial detail. The smoking gun of highly ionized oxygen and the primordial receipt from Big Bang nucleosynthesis confirmed the atoms must exist. The constant dialogue between supercomputer simulations and real sky observations has sharpened our search, guiding the design of revolutionary tools like XRISM, Athena, the Square Kilometer Array, and the next generation Very Large Array. Even the exotic possibilities of dark matter interactions or primordial black holes have been tested, narrowing the focus to the most probable answer. 25 interlocking clues from the first 3 minutes of time to the telescopes of tomorrow converge on a single, breathtaking reality. The missing baryons are not truly lost. They are spread throughout the cosmic web in a thin, hot plasma, a vast and hidden ocean connecting every galaxy. Solving this mystery is a testament to human curiosity and ingenuity, a decades-long detective story spanning the entire history of the universe. This story is not over. New telescopes will soon turn their gaze upward, and with each observation, the final map will come into sharper focus. You can be part of this discovery. Follow the missions, watch for the headlines, and stay curious. The universe has hidden half of itself in plain sight, and we are on the verge of bringing it all into the